Another example of being able to use the fundamental theorem of calculus to be able to find the exact area under a curve. So we have the integral from 1 to 4, 8x plus root x dx. So first thing we're going to do, let's set this up for anti-differentiation. And we're going to say that this is 1 to 4, 8x dx plus integral 1 to 4 of x to the 1/2 dx, just like we did with derivatives. Now we're going to find the antiderivative of both of these expressions. Right? So with the first one, remember you just add 1, divide by the new exponent. So this is going to be 8x squared divided by 2. And the second antiderivative, we're going to add 1 to 1/2. So that's going to be x to the 3/2 divided by 3/2. And that's going to range from 1 to 4. Now, clearly, the first term can simplify into 4x squared, which is really nice. And then remember the trick that you can just multiply by the reciprocal. So this is going to be 2/3 x to the 3/2. All right, and still going from 1 to 4 for our limits of integration. We're going to substitute 4. We're going to substitute 1. We're going to subtract. So we're going to get 4 times 4 squared plus 2/3 of 4 to the 3/2 power minus 4 times 1 squared plus 2/3 times 1 to the 3/2 power. All right, so this looks pretty intimidating because now we have these rational exponents, the 3/2 power. So let's just evaluate what we can. There's 3 easy ones, right? So we have 4 times 16. So that's just going to be 64. We're going to hold off on this, all right, because it's a little bit ugly, but it's not too bad. Anything 1 to any power is just 1. So this is going to be 4 times 1 and 2/3 times 1. So this is going to be 4 and then minus 2/3. And we can't forget that we have to distribute the negative. Now, what about this adamant? This 2/3 4 to the 3/2 power. So 4 to the 3/2 power, I'm just going to do this off to the side, is really just a radical. So 4 to the 3/2 is the same thing as the square root of 4 cubed. All right? Now, of course, you can use your calculator, but let's say for some reason you don't have your calculator. Well, this is just going to be 2 cubed, which is 8. Right? So it's really going to be 2 cubed times 8, or 2/3 times 8, excuse me. All right. And then we'll just go ahead and stick all of this in our calculator since we have a lot of denominators going on here. So that's going to be 64 plus 8 quantity 2/3 minus 4, and I think we had a minus 2/3. All right, we're going to hit math, enter, enter, and we get 194 over 3. All right, so let's hold on to that number because, of course, we want to make sure that that's right. So 194 over 3 is our answer. Okay, so now how do we know that we're right? Well, we're going to check it in the calculator. All right, so let's go into our math function. I'm going to hit 9. And I'm just going to say that we went from 1 to 4. And you might remember that the original function was 8x plus, I think it was the square root of x. Yep, 8x plus the square root of x. Okay. And we're going to integrate that with respect to x. Now we're hoping to get this 64.666. And we do, and then we can math enter it. All right, and this one's nice enough to give us the exact answer again. All right, so one of two things. We either got extremely lucky and we got the same answer just by chance, or the fundamental theorem of calculus actually works, and it's probably more likely that it works. One last example. Now, this is one a lot of students don't like because there's trigonometry, all right? And we have to get used to trigonometry because in Calculus 2, you're going to see a lot of trigonometry. So we have the integral from 0 to pi 6 of secant square of x dx. Right? Now, this one's actually not too bad because we could just rewrite this as 9 integral 0 to pi 6 of sec square x dx. And you might remember that if you take the derivative of tangent of x, that's sec square. So if I want to go backwards, the antiderivative of sec square is tangent. So this is going to be 9 tan of x from 0 to pi 6. Right? Now, this is where the power of calculus comes in, because if we throw this in our calculator, we're not going to get an exact answer. All right, so here's what we're going to do. We're just going to go ahead and use our fundamental theorem. So 9 tan of pi 6 minus 9 tan of 0. All right, so we're going to use our unit circle again. All right, so there's our unit circle to do some trigonometry with. At this point right here, which is 0, that's going to be the point 1, 0. All right, I don't think anyone doubts that because it's a unit circle. It has a radius of 1. And then right here, let's say that this is pi 6. Okay, at this point, you're going to have root 3 over 2 comma 1/2. All right, so hopefully from trigonometry, you remember your special angles, etc. Okay, and you might remember that the tangent is y over x on the unit circle. All right, so all we're going to do is we're going to say this is 9 times y, which is 1/2, divided by root 3 over 2. All right, so that's what this y over x, or the tangent of pi 6, can simplify into. All right, so tangent of pi 6 is this guy right here. And then we're going to get 9 tangents of y over x. So this one's a lot easier because tan of 0 is just going to be 0 over 1. So this is going to be 0 over 1. And we know that that's going to go away. A couple ways we can write this. We can write this as, because we have a 2 on the bottom, a 2 on the bottom, we can write this as 9 times 1 over root 3. And you might remember this from pre-calculus, that you can rationalize your denominator. So you get 9 times root 3 over 3. Or another way to write this, by simplifying, is 3 roots of 3. That's the most simplistic answer. Let's go through in the calculator. And we're going to run into some problems because, first of all, we might not even know how to put it in the calculator. All right, so we go to our calculator and we look around for our secant square button, and we don't see secant square. All right, and even if we went into the menu, we couldn't find a secant square. All right, so let me show you what to do to check this answer. All right, so another way to write 9 secant square is to rewrite it as 9 over cos square of x. All right, so you just use the reciprocal identity for secant. And another way to write cos square is just to write it as the quantity of cos x squared. All right, so what we could do in the calculator is we could just do our math and our 9. We're going to go from 0 to pi over 6. And we're going to say that this is going to be 9 divided by the quantity of cos x, close 1 parenthesis, close 2 parenthesis, square. All right, so notice that this is squaring the cosine function, and then we have to go over to dx. All right, now that gives us this lovely number, 5.196152423. Let's math enter it. Oh, well, that's because our calculator doesn't have the symbolic manipulator necessary to get to the answer. All right, so now what can we do to check the answer? Well, remember the answer that we got was 3 roots of 3. Okay, so if we go back here, couldn't we just approximate 3 roots of 3? And then maybe if it's the same thing, that means we're on the right track. So we could say 3 square roots of 3. We can hit enter. And lo and behold, those two numbers are identical to the 1, 2, 3, 4, 5, 6, 7, 8, 9 digit places. So we either again got extremely lucky or the fundamental theorem of calculus works. All right. And I've been teaching this for about 15 years, so I know that it works. All right. So hopefully this illustrates the power of calculus. All right. So if I was to graph this function and to look for the area under the curve, the exact area would be 3 roots of 3. There's not a calculator that's going to do that for us that doesn't have a computer algebra system in it. Okay, so this is one that we have to do by hand to make sure we're good with.